All right, everyone. Hopefully you are all doing well. We're going to be taking a look at the study guide questions um, for the test that we have tomorrow. I'm not going to be going over every single question. My goal here is to go over every single question type so as to be able to kind of cover what you would expect to see on something like the test that we have tomorrow. We're going to just kind of jump on in looking at number one. We are being asked to interpret an R value of negative 0.943. So the question is like, what does this mean? What does it tell us about the correlation? There are two main kind of pieces that we want to talk about whenever we are looking at a particular correlation. We can talk about the strength of the correlation, and we can talk about the direction of the correlation. Honestly, these two should probably be reversed. First and foremost, direction is the easiest to talk about. Because our R value is negative, we have a negative correlation. If our R value were positive, then we would instead have a positive correlation. So because we have this minus here, we have a negative correlation. Now, completely separate from whether or not what we are seeing is positive or negative, whether this value is positive or negative, is the strength of the correlation. The strength of the correlation does not care about the direction in which we see our correlation. So whether we have positive or negative correlation, instead, that is mostly going to focus on what is going on in terms of how close or how far this R value is to its kind of maximum possible value. R values are always going to live between -1 and 1. Think of an R value of 1 as being all of the dots just kind of perfectly in a line. You can draw a line that connects every single one of our dots. Exactly as you would see something like this. And an R value of -1, very similar, connecting all of our dots with a single line, but that line would then be going negative instead. So that's like perfect correlation, be -1 or 1, the strongest correlation we can get. The closer we are to that, the stronger, the better, quote unquote, we would expect that correlation to be. So we want to be close to -1 or 1, or rather, we want the absolute value of R to be close to 1. Right? Just so we don't have to worry about, are we talking about a negative correlation or a positive correlation? Nice to just take the absolute value, take the positive or negative out of the equation. And when we do that, 9, 4, 3, we are comparing 0.943, which is very close, I would say, to 1. Now we'll look later on, but this would then be the hypothesis testing. What does it mean to be close enough? Is this actually a strong enough correlation for us to claim that what we see is a correlation? And for our purposes, just descriptively, we would say that this is a strong correlation. I'm not going to give you an example on the test where it's not obviously strong or obviously weak. For instance, I wouldn't give you like 0.5 and ask you to tell me whether that's strong or weak. I would not give you like 0.6 or 0.4 or things like that. It'll very, very clearly either be strong or weak. All right. For our second problem, which actually is not number 2, but is instead number 3. We are being asked to figure out if what we are looking at is referring to causation or correlation. Now, first period had some really good questions about this particular topic. A couple of things that I want to highlight from that discussion. We only see causation. Of course, we have kind of our normal rules. Causation, we're looking for our buzzwords of things like experiment or study. And correlations are going to be everything. If we have causation, then we also have a correlation, but we have something even stronger than saying, oh, we just have a correlation. We have a more stringent kind of version. We have this causation. All right, so these are our buzzwords that we look for. If we see the buzzword, then we can go ahead and claim causation. If we don't see the buzzword, then it doesn't matter how certain we are that A is what is causing B to happen. We still just have to stick with correlation. That just is what it is. So for instance, looking at number 3, a recent study showed that there is a positive correlation between the number of DUI arrests and car accidents for adults over the age of 30. Because this was a study, we would say that this is, in fact, causation. Really, experiment is probably better, but we'll go with study as well. Study, it kind of implies to some degree some amount of experimental procedure. And so that is exactly what we see with this. Contrast that with, let's say, say, number 5. Number 5, I think, is an interesting one here. So in this case, number 5, we're told that there's a negative correlation between the number of cyclists that wear a helmet and the number of traumatic brain injuries from riding a bike. Now, it makes a lot of sense for us to say that wearing a helmet would reduce your likelihood of traumatic brain injury. That makes a ton of sense. Notice in this example, we don't know where this correlational data is coming from. We don't know if this is coming from an experiment or a study. Maybe it's just that bikers who are wearing helmets tend to drive safer. Maybe it's that bikers who wear helmets are more accustomed to biking, and maybe areas in which you have a bunch of people who are accustomed to biking, you have a lower incident rate of drivers causing people to crash. We don't have a definitive, clear-cut answer that the wearing the helmet is directly responsible for the prevention of the traumatic brain injury. Certainly that would make sense to us, but because an experiment has not been run, because a study has not been run, we cannot claim causation. The best we can say is that what we have is correlation. I think this is a really, really good example. Pay attention to number 5, where it makes a lot of sense for us to claim causation, right? It's not logically incorrect, but in this particular case, we simply do not have it. All right, so taking a look at number 8 here, we are trying to figure out which plot shows the strongest linear correlation. So remember, strength, like what we said before, this is our metric of not caring really about the direction of the correlation. Really strong is going to translate for us to be like tightly clustered. All right, there's not a lot of spread in what we see with the data. Now, things that I'd like to note, first of all, C and D, we've got a lot of randomness. So C and D, I would say, are very, very weak correlations, or more likely, probably no correlation, what we see there. So those don't make a whole lot of sense. This is going to be between A and B. A, which shows, I would say, a fairly clear positive correlation, and B, which is showing a fairly clear negative correlation. Again, the temptation is to say, okay, negative correlation is going to be worse than positive correlation, but positive and negative, that direction doesn't actually affect strength. And if we notice B, the clustering on B is a lot more kind of tight around this idea that what we are seeing is a line. It's a lot closer to forming a line. It's a lot less kind of spread apart. I would say that that is more tightly clustered. And so while A is a decently strong positive correlation, B is certainly a stronger negative correlation. Versus A, which would be like a moderately strong positive correlation. And again, there's not like an exact science to this. I mean, there is. We have numbers for it. But for our purposes, looking at that kind of idea of clustering. Okay, so taking a look at number 9 here. We are trying to figure out, get out my calculator. We're trying to figure out, based on the data from the table that has been given, various things. We're looking at the scatter plot, we're looking at positive negative correlation, all that fun stuff. To my stat mode, we're going to enter some 2 variable data. Go ahead and take a moment to plug all of this in. And then here for our y values as well. Pay attention to what has been defined as the x and the y. I'm not going to try and be tricky with it. It will generally be whatever comes first will be the x, whatever comes second will be the y. Just make sure that you are paying attention to what you are saying is x and what you are saying is y. That will certainly be important. Okay, so we are going to go to our stat option. We want to calculate the regression. I'm going to let you guys handle the whole idea of creating the scatter plot. But for my regression equation, I get the following, that y hat 9 is equal to, we say a plus bx. This is going to be 0.248 plus 0.222x, where r is equal to 0.8, sorry, not 8, but 985. Okay, so what can we determine? We're being asked to figure out if the data has a positive or negative correlation. You could do this from the scatter plot, but this r value very clearly is telling us that we have a positive correlation. We're also being asked to compute the correlation. Again, we already have that. That's our value of r. We have our equation. That's fantastic. And for 10 and 11, we're being asked to apply that equation. For number 10, we are given a number of cavities and being asked to figure out how much sugar has been consumed or would we expect to be consumed to result in that many cavities. Now, notice that cavities, or number of cavities, is our y value. And so substituting in number of cavities, which again is a y value, we can say that 2 should be equal to 0.248 plus 0.222 times x, and solving for x, this is going to be 1.752 is equal to 0.222x, and then dividing both sides. I get that x should be equal to calculate, want to calculate 1.7 I get that we would expect to see 7.892 grams of sugar consumed. All right. So given a y value, plugging in for y, we get this particular estimate, 7.892 grams of sugar. Conversely, if we are given an x value, for instance, with number 11, we're asked what happens when a child has consumed 13 pounds of sugar, which is our x. We plug that x value into our equation, y hat is equal to 0.248 plus 0.222 times this x value of 13, and we get the resulting y value, which is plus 0.222 13. I've summoned my creature. He is here to help me do math. And what he has found is that we have 3.134 cavities, or we would expect to find our estimated value for number of cavities would be 3.134. Now, of course, 3.134 does not really a good number of cavities that we would predict. We'll talk more about this as we go with 2.1, but you would expect a whole number of cavities here. So I would accept 3, but that doesn't mean that the 3.134 doesn't have value. We would say on average, we would expect probably close to 3, but maybe somewhere in between 3 and 4 cavities. More likely to be 3, but maybe somewhere in between 3 and 4. Okay. Number 12, 13, 14, those are all exactly the same. So let's then take a look at number 15. Okay. So in this case, we are given a set of data. We are trying to figure out, based on this data, do we have something that is statistically significant? Do we see a statistically significant linear correlation between these values? Okay. So we'll do, again, the x and the y. It's not super important which one is which, but we'll just do it this way that it is given to 6. Cat, you are not being helpful. Okay. And then we have 45.4, 8, 7, 44.6, 9, 7. Cool. Okay. So trying to run Okay, so trying to run our statistical analysis here. Ignore the graph. We did not talk about that. We will go into what is going on with that graph later on when we look at hypothesis testing again, which we will come back to. The whole use P thing as well, we're not going to focus too much on. What I want to focus on is the actual hypothesis statement that we can generate. So the hypotheses that we are going to be looking for, we have our null hypothesis and we have our alternative hypothesis. Null hypothesis, always, 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 is going to be that we see no correlation between these variables. And the alternative hypothesis is that we would see some correlation, that there is a correlation between these variables. Our assumption is that the null is true. Our goal is to try and prove that false. Right? As far as our critical value, we are looking at this particular table, trying to figure out the degrees of freedom. Remember that for, as it says on the table, degrees of freedom is just going to be sample size minus 2, which for our purposes, looking at the number of data points we are given, is going to be 6 minus 2, which gives us 4. So we have 4 degrees of freedom. The alpha value that we were told to use is 0.05. That is going to be standard with the alpha values that we would expect. Certainly, I could give you a different one. I'm probably not going to, though. That would be unnecessarily rude. And so the R value that we find that corresponds with a degrees of freedom of 4 and an alpha of 0.05 is going to be the R value of 0.81. Again, this is like our benchmark that we need to beat. More specifically, we would say that if we were to take 6 random data points that had no correlation between each other, we would expect to find an R value that's as strong as what we see here, about 5% of the time. And that 5% coming from that alpha value of 0.05. That's less important, but again, just kind of what this is saying. This is our minimum R value for which we are confident to say that there must be a correlation. We can't just keep pretending that there's nothing going on. Okay, so we have our critical value. We need to compare this with our test statistic. Sorry, bud. Does not like it. I am talking into his ear. It's okay. So we are going to stat. We are going to actually calculate the regression. And what I see here for my test statistic is we see an R value of 0.328. Okay. A pretty weak R value. Important to note, this could have been negative. It wouldn't matter. Again, we're looking at the strength. So the important thing to note is that this is weaker than 0.811. We are not seeing something that is particularly unlikely to happen. Our critical value is too strong, or rather our test value is too weak. And since it is weak, it is not good evidence. And so what can we say here? Well, we might say something along the lines of decision. Because our R value that we found was too weak, we have failed to reject the null hypothesis. So we assumed that the null hypothesis is true. We do not have enough evidence to suggest otherwise. That does not mean that the null hypothesis is true. Null hypothesis could still not be true. We have not proved that that is true. That would require a lot more. And in fact, we might never be able to verifiably prove that that is in fact the case. But all we are saying is we don't have enough evidence to say that it is false definitively. And so we might say something along the lines of there is insufficient evidence that there is a correlation, or if we just want to be simple, there is no evidence of correlation, or just that there is no correlation. There's no maybe strong evidence of correlation. I'm also fine with just no, there is no correlation. Again, it's a little bit too like, okay, we're kind of being a little bit too definitive when we say absolutely for a fact that there is no correlation. But again, it's kind of good enough for our purposes. All right, 16 is the exact same. Uh, 21 is the same thing that we saw from number 10, so that shouldn't be an issue. Let's look at number 22 here. This is kind of just like a sub piece of what we were dealing with. So using the table to kind of make these conclusions, figuring out, is the R value that we are looking at actually strong enough? Do we have enough evidence? So let's take a look at, for instance, we'll do a surprising one. Let's take a look at, I think 23 is a good one, where we are told that our, again, for an alpha of 0.05, where n is equal to 17, is a test statistic of 0. of r is equal to 0.478 actually strong enough. At first glance, this does not seem particularly strong. And actually, the table that I have does not go that far, but that's fine. We can Google PPMC table. I go to images here. It's kind of the nice thing about these tables is we just need to be careful. Are they talking about degrees of freedom, or are they talking about something else? And what we see, we want to make sure we're doing our two-tailed test, is that when we have, if n is equal to 17, then notice that our degrees of freedom should be equal to 15. Again, that's just n minus 2. And for a two-tailed test at an alpha value of 0.05, the metric to beat, the critical value, which again, I'm just getting by looking it up in a table that I found online. I would provide you this obviously on the test, but the metric to beat is 0.482. So actually very, 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 very close. These are not all that different. And for an alpha value that was maybe a little bit less stringent than 5%, maybe we would have enough evidence to suggest that what we see is a correlation. But again, notice that this test value is weaker than our critical value. And so we would again fail to reject. And you could do that with each of these. Would that be, I don't think that's an example where you could accept. That one's probably an example where you would accept. Is it? Yeah. 24 would be an example where we do actually have enough evidence. So for 24, we would have 30 degrees of freedom, where our R value that we are trying to beat is, let me pull up the table that I was looking at. This would be 0.349. Notice that our R value of negative 0.43 is in fact stronger than what we see with the negative 0.349. Okay, one more question, and then we will call this done. So looking at number 25, trying to figure out which of the following statements is true. Or we'll just go ahead and say whether what we are given is true or false. So looking at the first statement, if a linear correlation coefficient of two variables is 0, then there is no relationship. So we know that if we see a positive correlation coefficient, that we have a positive correlation. If we see a negative correlation coefficient, then we have a negative correlation. And in fact, it is true that if we have a correlation coefficient of 0, that there is no correlation that is a true statement. Right, for number 2, if the slope of the regression line is negative, then the correlation coefficient is also negative, and vice versa. The kind of equivalently true statement, if the slope are positive, then the correlation would be positive. This is also going to be true. The negative correlation coefficient tells us that as our x gets larger, the y gets smaller on average, and trends for which that is going to be true are going to be trends that have a negative slope. Something like this, right? So that negative trend will in fact result in a negative slope, and so that is true. Likewise, positive trend will result in a positive slope. So definitely true. Number 3, the value of the correlation coefficient always lies between -1 and 1. We say that this is true. That -1 to 1 is because the correlation coefficient says something, we're not going to get into the weeds of this, about the percentage of the data captured by the line. It's actually not the R value itself that says this, but there's a piece of the R value, or a thing that we can do to the R value that will give us that information. The maximum amount of data that can fall on our regression line is 100% of the data. Therefore, having an R value that is greater than 1 would not make much sense. That's basically saying that of all the data that we have, plus more data that we don't even have, all of it is falling on the regression line. That simply doesn't make sense. The most amount of data that can fall on the regression line is 100%, and so 100% would be the highest R value that we could see. Again, that R value is not saying that, but there's a very easy kind of way to get that information from the R value, and so the R value again might as well be saying that. Okay, last one, linear correlation coefficient of 0.62 suggests a stronger linear relationship than the coefficient of -0.82, and hopefully by the end of this, we can very, very quickly say that this is certainly false. Again, the positive, negative, none of that matters when what we're looking at is strength. Instead, the only thing that we are focusing on in terms of the strength of the relationship is whether it's close to 1 or -1 versus being close to 0. Notice that when we take the absolute values of both of them, because again, we don't care about the positive or negative, when we take the absolute values, how 0.82 is closer to 1 than 0.62. Therefore, or maybe better, that this absolute value is greater than what we see here, and therefore this is strong. Whether it's positive, whether it's negative, it doesn't matter. I saw that on the quiz a fair bit. A lot of people put for the strongest R value, they put the strongest positive R value, but there was a negative R value that in fact was even stronger. All right, hopefully that helped clarify any misconceptions that we may have had. If you have any questions, of course, feel free to reach out. Remember that the classwork is due by 7 a.m. tomorrow. And the homework as well, not this packet, but the one that has the crossword on the front. Not extra credit, that is in fact a homework assignment. Make sure that that is all wrapped up by then. I wish you all the best in terms of studying. You are all more than capable of doing this. I have a lot of confidence in your ability to do well on this test. And beyond that, hope you all take care and have a good rest of your evening.